Hey guys, welcome to Safi Mixed. In this video, I want to apply Newton's second law to solve the problem of what we call Atwood's machine. Atwood's machine is an important problem which is an integral part of almost every book written on introductory courses on mechanics. It is uh, It is important because it gives an insight how to write mathematical equations for a model, and it is used in fact to measure the value of G experimentally in lab. So it is a good exercise for students of introductory courses in mechanics. In reality, it is a complicated problem, but we put certain constraints, under certain assumption, we reduce the problem to an ideal case, which is then enable us to find the easy solutions. So, what is in fact this? This is a Atwood machine is a pulley hang from a support, and a string is passed over it in two masses M2 and M1 are attached to the ends of the string. Now, if the mass of the pulley is considered, then it has moment of inertia, and if the whole apparatus is enclosed inside a box, and the box is placed in a reference frame that is moving with certain acceleration, then that would be either in the upward direction, downward direction, or horizontally forward or backward, whatever the acceleration may be. That acceleration then obviously contribute to the whole dynamics of the Atwood machine. But I will solve this problem under the very simplified conditions. That is, I consider the pulley to be of negligible mass, and that would give me I, the moment of inertia, equals 0. Secondly, I consider that the rope is inextensible, and if the rope is inextensible, that means the acceleration of this mass is exactly equal to the acceleration of this mass. So if the rope is inextensible, that means the acceleration of A1 is exactly equal to the acceleration of mass A2. The acceleration A1 is exactly equal to acceleration A2 of the masses. So we have now put two conditions. Number first, the moment of inertia of the pulley is 0. Number second, the rope is inextensible, that allows us to write the acceleration of the two masses equal. And I made another example that there is no friction in the system. If there is friction, let the tension in this side I denote with T2, and the tension in this side I denote with T1. If there is friction, then I would write T2 equals T1 plus F, because some part of the tension would be used to overcome this friction. And if the friction is 0, then this part is 0, and we are left that T2 equals T1. So I solve the problem under this condition, that is, I consider the friction to be 0. So with these three constraints, it is now a very highly simplified problem, however far away from the real cases. And then I take a reference point, the ground be the reference point, or this support could be the reference point, and I locate the positions of the two masses with respect to the ground. Let this be x1 and this be x2. Then I find the net forces on each mass, and for that I consider that the downward direction is positive. So I take the downward direction positive. You can take the upward direction positive or the downward direction positive. And secondly, as obvious from the diagram, M2 is greater than M1. So under these conditions, the net force acting on this body is in fact equal to M2G, that is the weight, minus T2. And according to Newton's second law, this net force must be equal to mass times acceleration of body 2. And for this case, I can write T1 would be greater, since this would be moving in upward direction, T1 minus M1G equals M1, this is M2, M1 times A1. This is equation 1 and this is equation 2. Now, if I use this condition T2 equals T1, then that means I can set each T1 into 2 equal to T, and then this equation reduces to this thing into this thing. And if I employ this condition, that means the acceleration are same and I replace A1 and A2 with A, so I will drop this subscript and this subscript. Now the equation are very simplified by using these two conditions, and if I add these two equations, then the T would cancel and I'd be able to write M2 minus M1, taking G common from this side, equals M1 plus M2 times A. And I can straight away write the acceleration in terms of M2 minus M1 divided by M1 plus M2 into A. Sorry, not A, G. Right? Since we have considered that M2 is greater than M1, therefore this thing is positive. M2 is greater than 1, that is positive. So A is positive, it is in the downward direction. And then obviously the acceleration of the mass M1 is in upward direction. So if I count the direction, then I can write A1 equals minus A2. The vector, in the vector form, I can write it like this. That is, if the acceleration A1 is downward, which is positive, then the acceleration A2 is upward, which is negative. So that's only the change in direction, and we represent in vector form the change in direction with that negative sign. Now, if I look at this side, we know everything on this side. We know masses, and we know the acceleration due to gravity, so we can find A. On the other hand, if we want to find G, we can measure A by the setup of this equation and can find G, that is the acceleration due to gravity. We can calculate experimentally the acceleration due to gravity by using Atwood's machine. Now, using the value of A in either of these two equations, 1 or 2, I can find the relation for tension. I call this equation 3 because I want to use this equation for other purposes. So I remove the conditions, and from equation A, I can write, rather from equation 2, I can write T equals M1 common A plus G. Because I'm taking this to this side, so it will become plus, and then I'm taking M1 common to write it in this form. And if I substitute the value of A over here, I can then write this as T equals M1 times this thing, M2 minus M1 divided by M1 plus M2 times G. This is the value of A, and then plus G. I can take G common and can take the LCM of these two terms to put this in the form M1 into M2 minus M1, and then multiplying this with this would make it M1 plus M2 the whole divided with M1 plus M2, and taking G common from the two terms. This goes with this, allowing me to write this as 2 times M2 M1, 2 times, because M2 plus M2 is 2, and then I'm multiplying this, so 2 M1 M2 divided by M1 plus M2 times G. And what do we see over here? This is tension. From this, let me call this equation 4. Now, from equation 3, if the two masses are equal, the acceleration is 0. Right? Acceleration is zero mean if the system is initially stationary, it will remain stationary, and if we give a push to put this in with certain acceleration, so with certain velocity, it will continue with uniform velocity, applying Newton's first law. On the other hand, if the two masses are equal, this would give me m1 equals m2 equals m, so this would give me 2 times m squared, and this would give me, so that would reduce to 2 times m squared divided by 2m. The 2 cancel and multiplied with g, the 2 cancel with 2, and the square cancel with this, and then this is equal to mg. Exactly, that would be equal to mass m on both sides, so that this tension would be equal to mg, this tension would be equal to mg. That is, the tension in either side would exactly be equal to mass times g. Now, that is what we see from from this equation. In this equation, I can find velocity by writing a equal to dv over dt equal this whole thing. Let me call this whole thing c, because these are constant. Then I can write this equation in the form dv equals c times dt, and I can integrate this between certain initial velocity. That is, I suppose that initially the velocity is 0 at time t equal to 0. Then this gives me v of t. Then this gives me dv integrated from 0 to v of t equals c times 0 to t dt. And this obviously gives me v of t from 0 to, this obviously gave me v from 0 to v of t equals c of t from 0 to t. And putting the values, I can write v of t equals ct. And similarly, if I integrate this one more time by writing vt as dx of t over dt equals c of t, then I can separate them to write this in the form of dx of t equals ct dt. And then I can integrate this with respect to either x1 or x2, whichever you may take. I can write this as integral dx from x, let me call that x naught, to x of t equal ct integral from 0 to t dt. And this obviously gives me x of t equals x naught plus c divided by 2 t squared. Then this equation gives us the position with respect to the ground of either this particle or this particle. So this way we find the dynamics of the masses attached to a pulley. That is, we solve the Atwood's machine under the conditions that neither the string is extensible, the mass of the pulley is negligible, and the friction is 0. Under these three conditions, we have this equation for the dynamics of the masses. Thanks for watching.